So today is going to be our second lecture on bottom-up parsing, in particular LR1 parsing. So LR1 parsing is a one specific type of bottom-up parsing. In the first lecture we introduced bottom-up parsing, the idea of bottom-up parsing, and how bottom-up parsing differs from top-down parsing. And we also showed how a bottom-up parser processes a string, but we did not, the part that is missing, that was missing in the first lecture, is how the parser systematically makes decisions. And what's the decision that a bottom-up parser has to make? What's the main decision that a bottom-up parser has to make based on last lecture? So it has to make an important decision to choose between two options, two main options. What are the two main options in bottom-up parsing?
So you can shift or reduce.
Yeah, exactly. So it's about shifting or reducing. Should we shift or reduce? Now, what does shifting mean?
Take
Yeah, Theodore. Yes.
a symbol from the input and putting it on the stack.
Yeah, exactly. So get the next symbol from the input and put it on the stack. So we have to systematically decide, we have to have a way of deciding whether to shift or reduce. But suppose that we decide to reduce. Is that it? No. So it's not sufficient to decide that we need to reduce. What should we specifically decide? So
Which production? Reduce this production.
Yeah, reduce by which production? So for reduction, a reduction may happen using multiple productions, and we should decide which production to use. So if at some point the parser doesn't know whether to shift or to reduce, if both options are possible, then LR1 parsing doesn't work on this grammar. The options are: try to restructure the grammar. Maybe you can make it work with LR1, and maybe you cannot. Maybe this language is not parsable by LR1 because LR1 does not parse all the languages, all the context-free languages. And also, if you decide to reduce, but there are multiple productions by which you can reduce, again, you haven't made a clear decision, and there are multiple options. So in this case, LR1 parsing also fails. Okay. So now in today's lecture, we'll take this simple example. It's probably the simplest non-trivial example that will illustrate this technique, and we will see how LR1 and LR1 parser, how it constructs the tables that will tell it whether to shift or reduce, and reduce by which rule. So this is what we will be spending most of our time today doing. Okay. Now again, remember that when we are doing LR1 parsing, this is your input string, and you are pointing at this point. So this is the start of this is going to be the symbols that you have not read yet, and what you have read will be on the stack, but it will not necessarily be in the form of terminals, right? What's on the stack will be what? What's on the stack in LR1 parsing is not necessarily terminals. It's no. Well, at this level, terminals are tokens. So forget about scanning. We have scanned, and all of our terminals are now tokens. But what we have on the stack, if you go back to last lecture, is not necessarily a terminal. It may be a non-terminal, because we may have made some reductions. So what's on the stack? The stack has terminals and non-terminals, a mix of terminals and non-terminals. But what we haven't processed yet is only a bunch of terminals. So we have, in this parsing, we have a prefix and a suffix. So the suffix is the part that we haven't processed yet, and it will consist entirely of terminals. But the part that we have processed is now on the stack, but it's a mix of terminals in general. It's a mix of terminals and non-terminals. So this is the stack, and the stack has a mix of terminals and non-terminals. And why does the stack have a mix? Because we may have made some reductions. So every reduction that we make will introduce a non-terminal. Okay, so now how do we do this? Well, like we said last time, we track the progress that we are making on all productions in the grammar. So our start state, state 0, in this case, is going to be, or let's put it here. State 0 is going to be this. Goal. So this is going to be the first. This is going to be the first item in every initial state. Goal, and we are in the beginning of A. Then our look ahead is going to be what? So in order to make this reduction from A to goal, what should be the next? When we make this reduction from A to goal, what should the next symbol be?
End of file.
End of file. Because this is something that you will make only once at the very end. At the very end, you will make it only once, and your look ahead should be an end of file. So this is our format for what we call an LR1 item. So this thing is an LR1 item. An LR1 item is more than a production. It's a production with two things that we add. The first thing is this, which is what? This period, which is
The placeholder.
yeah, it's the placemaker, which means that we are right at the beginning of this, and this is the look ahead. So we are adding this placemaker and this look ahead. Okay. Now, when we are at the beginning of an A, we have to look at the lower level rules to see where we can possibly be in those rules. Because we are about to, this means that we are expecting an A. We haven't matched anything yet, and we are expecting an A. So if we can recognize an A, then we can make the reduction and we are done. But we should look at the rules that define an A. So at the second level, we should look at all the rules that define an A. So an A could be an AA, or it can be an A. Now the look ahead is going to be the same. The look ahead is going to be the same because if we recognize an AA, it should, this A. So this is what should appear after an A if we make this reduction. And what appears after an A will be an end of file as well. Now, are we done? No, we are not. This procedure, which we call the closure of this state, we should continue doing this until, as long as there are non-terminals with a placeholder in front of it. So here, this is an A, and this is the placeholder before the A. So in this case, again, we should look at all definitions of A. But now, our look ahead is an A, not an end of file. It means that we are expecting an A followed by an A. And this A is going to come from the definitions. So this is basically, level 0. This is level 1. This is level 2. At level 2, this A will come from an AA, or it may come from an A, but it should be followed by an A. So why are we doing this? We are doing this because what comes after an A may be an end of file. It could be an end of file. It could be an A, depending on the level at which we are making the reduction. So this reduction can be made at multiple levels. And at each level, there will be a different a different symbol that follows it. So this look ahead is this look ahead must belong to the follow set of this. So the look ahead here must belong to the follow set of this non-terminal that we are defining. So for example, if we are deriving, let's look at the derivation for AAA. Derivation for AAA is going to be goal is an A, and the A is an A, and then A is an A, and then what's the last substitution? This is a single A. What does this mean? It means that this reduction, from an AA to an A, we did this reduction at different levels, but what comes after the A is different. So here we have an AA, but what comes after it, and the look ahead that we should be looking for in the input, is going to be an A, because this is the A. So this is an AA followed by an A, while this is an AA followed by an end of file. So there are multiple possible followers, multiple possible look aheads for this particular production. So now what's the follower of this? We are substituting an A for an A. What's the follower of this? So what comes after this? An A. Does this mean that the A will always be followed by an A? So why do we have this? So here we are making this reduction, but we have an end of file. So which means that this may be possible. When is this possible?
You just have a single A.
Exactly. If you have a single A, you will have this. Goal, A, then A. Now what's the follower of this A? It's end of file. So what we have, this closure tries to find all possibilities, including, this is the top level production. This is the next level. But for the next level, there is also another level. And at this level, the follow may be different than the follow or the look ahead at this level. Okay. Now, this is our start state. Now, how can we make progress? We can make progress if we see an A, a small a, or a big A. So if we see a big A, if we can recognize a big A, then we will make the following progress. Now with an A, we will look at those productions in which the placeholder appears before an A. So we look at this and this, but we will not look at this because this is placeholder small a. This is placeholder big A, and this is placeholder small a. So these are the three ones that we care about. So when we make progress, when we recognize an A, we will get goal, A and end of file. Then, if we make a progress on this, we will get A, what? A, placeholder A. So if the point is, if we recognize an A, we are making progress on this, and we'll get to this point. We will make a progress on this, and we'll get here with an end of file. And we will make progress on this, and we will become here with an A. So, well, we shouldn't close this yet, because in general we should look at the closure of this. Now the closure, to find the closure, we look at the placeholder and see if there is a placeholder followed by a non-terminal. So do we have a placeholder followed by a non-terminal? No. So this is placeholder followed by nothing, placeholder followed by a terminal, followed by a terminal. If we had a placeholder followed by a terminal, like, for example, A dot X A, then we should continue, and we should look for the rules for defining what? We should put the rules or productions for defining X. Then we should put all the rules for defining X. And there may be multiple rules for defining X. Now what will be the follow for this X? It will be an A. So all the rules for defining X followed by an A. Now, what if we had something like this? A, then A, X, Y, A. Now, in this case, to continue to find the closure of this, we should find all the rules that define X. And now, what will the look ahead be?
The first one.
The look ahead should be what? So what comes after an X? The question is, we're looking for an X to recognize. But what comes after an X? A Y. So we should look at the first set of the Y. So this should be like if the first of Y equals B and epsilon. And suppose that we have two rules for defining X. Suppose that we have X goes to alpha and X goes to beta. Then here, if we have X goes to alpha and X goes to beta, and we have this is the first set of Y, then now we will have X goes to alpha followed by a B, X goes to alpha followed by an A. Why an A? Because Y may be epsilon. Okay, so X goes to alpha followed by an A, and X goes to beta followed by a B, and X goes to beta followed by an A. So we should cover all the rules for defining X, and then for each rule we should cover all the possible followers of X. So in this case, all the followers of X are going to be anything in the first set of Y. But if Y has epsilon in its first set, we should look at A, because if Y is an epsilon, what comes after X could be an A. Because we are trying to find to answer the question, when will it be possible to make this reduction? What should the look ahead be in order for a reduction to be valid? Okay, so this is how we compute this closure. The closure may be the part that most students find the hardest. And usually students miss something in the closure. So the general rule for for finding the look ahead, if you have a rule like this, x is alpha or let's say beta equals beta c dot gamma with a look ahead of a, then in this case, sorry, it's this is here. Then the closure for this is going to be all the rules that define C. So there may be one or more rules that define C. And for each one of these rules, you should have the look-aheads of first of gamma A. First of gamma A is equal to first of gamma. First of gamma if first of gamma does not have epsilon. Okay, first of gamma A equals first of gamma if epsilon does not belong to first of gamma and is equal to first of gamma minus epsilon union A otherwise. Meaning that if this thing can go to epsilon, you should include this. Okay? So this is how we compute the. But here we don't have any placeholder preceding a non-terminal. Now, if we get an A. Now, if we get a B, if we get a small a, then what should we have here? With a small a, we should look at the other rules, the rules that have a placeholder preceding an a. So if we make progress here, what will we get? A placeholder, end of file, yes. And when we make progress, yeah, A placeholder A. Okay. Now this state, if we reach this state, if we reach a state like this, and let's call them, let's call this S0, this is S1, and this is S2. If we reach S2, and our look ahead is either end of file or A, then this means that we have recognized enough now to make this reduction. So when the placeholder reaches the end of a production, this means that what we have recognized so far is ready for a reduction. Okay. When the placeholder gets to the end of a production, it means that we have recognized enough to make up a reduction. So we are ready to make this reduction. And in this case, we reduce. So this is a reduction by which rule? Rule number 2. So we call it R2, which means reduction reduced by rule 2. Okay. So R2 means reduce by rule 2. And this is also another reduction by the same rule. So what does this tell us? It tells us that this reduction is valid if the look ahead is either end of file or A. Of course, it may look like okay, in this case, there are only two possibilities for the look ahead, because we only have small a and end of file. But in general, this will not be the case. So in general, sigma can have many other symbols. Okay. Now, do we have a reduction here? Do we have a possibility of a reduction here? Yeah. So reduction means the placeholder appears at the end of a production, and it appears at the end of this production. So this means that we are ready to make a reduction. And this is the by rule 0. So this is the big reduction, R0. And when we reduce by rule 0, we call it accept, because rule 0 is the final substitution which reduces to goal. So this is an accept. We are done when we get there. Now we'll see how we can use this to do the actual parsing. Okay. So now, now this, because the placeholder here reached the end, in all productions, this is going to be a leaf state. Nothing can come after this, because the placeholder cannot go any further. It cannot go beyond this point. It has just reached the end. But this is not the case here, because here the placeholder reached the end of this production, but it hasn't reached the end of these. So there is still further progress that we can make here, because the placeholder is still in the middle here. So now what should be the label of this transition? Small a or big A?
Small a.
Small a. Because if we get a big A, there is no progress here on a big A. But there is progress on a small a because of this placeholder. This placeholder is moving, is tracking our progress. So with this placeholder, we will make progress. And this A becomes A dot, placeholder, end of file. And what else? A small a, placeholder A. Okay? Now, do we have a reduction here? Yeah, we have two reductions because the placeholder reached the end of the production. We have a reduction. So we can reduce here, reduce by rule number 1. So this is an R1, this is another R1. Reducing by rule 1, reducing by rule 2, reducing by rule 0, which is an accept. Okay, and let's name this state 3. This is our state 3. Okay. So these placeholders are tracking our progress. So generally speaking, when you have, x is alpha, placeholder, beta, and here you have the look ahead, which is not necessarily a. You can call it, little x. What does this mean? When we have something like this, it means that what we have recognized so far, we have recognized an alpha. Remember that this placeholder is the boundary between the stack and what we have yet to read from the input. So this is, alpha is on the stack. When you have a placeholder like this, in this position, it means what's on the stack is an alpha. By the way, when we use the Greek letters, it means that this could be multiple symbols. So this alpha could be, multiple non-terminals. In fact, non-terminals and terminals. So But this alpha is what we have on the stack. Beta is something that we expect. This is what we expect. If what we have, what we have to read next, if what we read next ends up being a beta, if we recognize a beta, then we are ready to make a reduction. So if in the next state we get x alpha beta placeholder x, this means that now we have recognized both an alpha and a beta. So if we get here, OK, so here our stack is going to have an alpha. Here our stack is going to have an alpha, but there is a beta on top of it. So this is the, the dot is the corresponds to the top of the stack. If we get to this point, we are ready to make a reduction if
the look ahead is x.
If the look ahead is x. Yeah, exactly. If the look ahead is x, we are ready to make this reduction. This reduction is now valid. If what we are seeing in the input is not an x, this reduction is not valid. We can't make this reduction. OK? So this is the, the logic of the placeholder. And by doing this, we are tracking all possibilities. Now let's see how we can use this to construct what we call the action table and the go-to table. So the go-to table is very easy here. The go-to table is going to have the states, and we have 4 of them. So the go-to table, or let me move it a little bit so that I can have more space. OK, in this case, it's going to have S0, S1, S2, S3. And OK. And this is S0, S1. And the columns are going to represent non-terminals. And in this grammar, the only non-terminal is an A. And the only valid transition is that if I am in S0 and I get an A, I go to S1. But out of this is an A. Out of S1 or S2 or S3, there is no transition on a non-terminal. So the only state that has an outgoing transition with a non-terminal in it is S0. So the only entry in the go-to table here will be on A. If I'm in S0 and I get an A, I go to S1. Now let's do what we call the action table. OK, I'm going to put the action table here. The action table. OK, so let's see the logic of the action table is that I have these states, S0, S1, S2, S3. And I need to make an action based on the look ahead. And my look ahead in this example could be an A or end of file. So the columns in the action table are going to be terminals or end of file. OK, with a terminal and end of file. Now, if I'm in S0 and I get an A, what does this mean? Go to S2. So if I am in S0 and I get an A, I'm not ready to make a reduction. So I go to S2, and this is a shift. So I shift and go to S2. So this S here stands for shift. the S in the action table stands for a shift. Shift and go to S2. So this tells me that if I get an A, then I have to shift. If there had been a reduction here, with A being the look ahead, this would have been a shift reduce error. Two possibilities. There are two valid possibilities. So if I had a something like this, if I had a placeholder here, with a placeholder here and the look ahead being an A, it means that if I get here and my look ahead is an A, I can reduce. But if I can reduce and I can shift at the same time, this means that the LR1 parsing fails. So I can't do it with LR1. I have to either modify my grammar or look for a different parsing technique. This is a shift reduce error. So in every step, there should be a unique valid action. Only one valid action, either a shift or a reduce. And if it's a reduce, it has to be only one reduce. I can't have multiple reductions. So I can't have, for example, this reduction, and they both appear on an A. If I have something like this place, so I can reduce by this on an A when the look ahead is A, and I can reduce by this with the look ahead is A. This is going to be a reduce error because there are two valid reductions, and this is bad. It means that we can't do this with LR1. This grammar is not LR1. So either modify the grammar, try to make it LR1 if you can, or use a different parsing technique. OK, so now the only action that is valid is a shift. For an S1, if I get an end of file here and I am in, there is no transition on an end of file, and there is no reduction. If I'm in S1 and I get an A, so I just follow this. This is S1 and this is transition on A. If I transition to another state, this is what? This is the shift. So I shift and go to S3. Now, if I am in S1 and I get an end of file, yeah, I do a reduction. This is a valid reduction. So I do an accept. So this particular reduction is an accept reduction. Now, if I'm in S2 and I get an A, then if you are in S2 and you get an A, the look ahead is an A, you reduce by 2. What if I get an end of file? Same thing. Reduce by rule number 2. If you are in S3 and you get an A, this is S3. So if you get an A or an end of file, you are ready to make a reduction. And again, you reduce by rule number 1. OK? So let me put the go-to table here. S0 on an A goes to S1, and then S1, S2, S3. I don't go on any state. OK, so now let's trace. Let's see how we can parse AA. How can we parse AA? We start at the start state. So step number 1 is S0. You push the start state on the stack. Our initial state is S0, the start state. Now we go to the action table. The action table tells us what to do. And since we managed to construct the action table, and there is always one unique valid action, it means that we always know what to do, to shift or reduce, and reduce by which rule. So OK, S0, and what's my look ahead? My look ahead is A. I am in S0 and my look ahead is A. It tells you to shift and go to state number 2. So you're going to do shift, which means read the A. The A is on the stack, and I am now in state number 2. OK, now I'm in state number 2. State number 2, and state number 2, and my look ahead is an A. Now what should I do if I am in state number 2 and my look ahead is an A?
Used by rule 2.
Yeah. So you are in state number 2 and your look ahead is A, then you reduce. Sorry, since I shifted, so I'm here. But the look ahead is still an A. So if I'm in S2 and with an A, S2 and an A reduce by rule number 2. Rule number 2 is this. So I make a reduction. So now what I reduce by is going to be, I pop these off the stack. So this is a tricky part. I pop these off the stack, and then my go-to is going to depend on what remains after the popping. So I will go back to S0. So I will look at go-to of S0, and the non-terminal that I get with this reduction. Reduction 2 will give me what? An A. Reduction 2 will give me a non-terminal A. So go to S0 and A. So we consult the go-to table when we make a reduction. We consult the go-to table after popping this off. So we go to the original state, which is S0. So S0, the go-to of S0 and A is S1. So this tells you to go to S1. So you push the A, and you are now in S1. So again, this is a tricky part to decide, which state to go to after you make a reduction. And this is the first, the purpose of the go-to table. The go-to table tells you which state to go to after after you make a reduction. And the state is going to be determined by the state after you pop off this, the symbol and the state number. After you pop them off, this gives you S0. And the column is going to be the column that corresponds to the non-terminal that I get by this particular reduction, which is in this case R2. It will give me an A. So go-to of S0 and A is going to be S1. So I'm now in S1. So I'm now in S1 and I'm seeing an A. So if you are in S1 and you are seeing an A, what does this tell you? Shift to S3. Shift to S3. So it tells you go to S3, so you will shift. Now my stack is getting bigger. So I have S0, A, S1, and I'm shifting. So I'm going to another state with an A and an S3. This is what I have on the stack now after the shift. OK? So this is, this is shift. This is an S2. This is an R2. This is an S3. Now, I am in S3, and I'm seeing an A. So you consult the table. If I am in S3, and I'm seeing an A, I'm in S3, and I'm seeing an A, what should I do? The table tells you reduce by 1. OK. So I reduce by 1. So this is the next step, Now, when I do a reduction, when I make this reduction, I have to be careful. So when I reduce by 1, 1 tells me to replace A with an A. So how many entries will I be popping off? 4. Because I will be popping off the symbols and the states. So I will pop all of this off. All of this will get popped off. So my state, my base state is going to be S0 now. So I should go to S0 and the non-terminal that will be the outcome of the reduction, which is I reduce to an A. So go to S0 and A, and this is going to be go to of S0 and A is going to be S1. OK? So this means that after doing this, I will be, OK, this is S0. Then I will put the A. And now I am in S1. OK? By the way, what did we forget? We forgot something. So when we shifted here, we did 2 shifts. So the first shift got us here. The second shift got us here. So now our look ahead is end of file. So now I am in S1. I'm in S1 and I'm seeing end of file. So this tells you accept. You are done. OK? So now with S1 and the look ahead is end of file, then this tells you to accept. So now I'm S0, goal, and in fact, this is in fact, I'm in the accept state, so it's an accept. So in fact, there is an implicit accept state here. So this puts me in the accept state. Now, to summarize how all of this works, well, first of all, I construct these states. And the trickiest part is what we call the closure, which means for every placeholder that appears before a non-terminal, I have to put all the definitions, all the productions that define that non-terminal, and I have to carefully decide what the look ahead is going to be. The look ahead is going to depend on what comes after this symbol. So it's going to be the first of this followed by this. If this has an epsilon in it, I look at this. It's going to be the end of file. OK. Then to use these tables for doing the actual parsing, you first push S0. Then you just consult the table. The table tells you whether to shift or reduce. If it's a reduction, it tells you which rule to use, which production to use for reduction. If it's a shift, it tells you which state you should go to. Now, when do I use the go-to table?
After reducing?
Yeah, exactly. The go-to table is used after a reduction. It tells me which state to go to after a reduction. And why are the columns in the go-to table, why are they non-terminals?
Because you look up the terminal that you just reduced.
Yeah, so I look up the non-terminal that I reduced to. So whenever you reduce to something, you reduce to a non-terminal. So this is the non-terminal that you reduce to. And this is the state. Now, the base state that you use for lookup in the go-to table, where does it come from?
The current state.
So where does the state that which state do you use to look up the next state in the go-to table?
State that you get after you pop.
Yeah, remember that it's the state that you get after popping off. And how many items, how many entries on the stack will you be popping off? It's the number of symbols in the reduction multiplied by 2. Whatever the number of symbols in the reduction or in the production that you are using is, multiplied by 2. Why multiplied by 2? Because you have to include the states themselves. OK? So as you can see, LR1 parsing is it involves a lot of bookkeeping. So that's why it's in practice it's automated. So there are tools that do this for us. And we spent a whole lecture showing how to do LR1 parsing for the simplest possible grammar. So we can't have a simpler non-trivial grammar. This is the simplest example, and it took a whole lecture. So in the next lecture, we will see another example, but we will not get the chance to do everything. So we'll do part of it. OK? Any questions? Okay, so I hope that it makes sense.